solve oblique triangles using the law of sines. Any triangle that's not a right triangle is called an oblique triangle. What we want to do is give you some of the sides and angles, and you give us the remaining sides and angles. And one method to do this is using the law of sines. Where the law of sines comes from is you take an arbitrary oblique triangle and you drop a perpendicular a height. And you notice that what can happen is that if you go ahead and just take a look at this triangle here on the left, that if I looked at the triangle, the sine of A, which I know is opposite over hypotenuse, would be h over b. And if I looked at the triangle that I've created on the left, which is also a right triangle, then the sine of b would be equal to opposite over hypotenuse, and that's h over a. So all I'm going to do is solve for h in each equation. I'm going to solve for h in each equation. Well, look at the equation on the left. I'd multiply both sides by the denominator, which is
b.
And that leaves b what? b
sine a.
And that's equal to h.
Right.
But see, h is also equal to what if I multiply both sides of the equation on the right by a? It's equal to?
A sine b.
Very good. Now, both of these are representations for what? For h. So we can set them equal. We can say b sine of a is equal to a sine of b. And the law of sines is a really nice rubric to remember. And where it comes from is this step. I'm going to divide both sides of the equation by ab. And when I do, what cancels on the left?
The
B.
b's.
What cancels on the right?
The a's.
Very good. So we end up with the sine of a over little a, which is the length of the side of a, and that's equal to the sine of b over little b, which is the length of the side of b. And a and b were arbitrary. So we can extend that to any pair of angle and opposite sides. So I can say that my law of sines is nothing more than sine of a over a, which is equal to sine of b over b, which is equal to sine of c over c. Easy enough to remember. How do we use it? Wonderful question. This is how we use it. Suppose we have alpha is equal to 30 degrees. So I'm going to go ahead and mark that 30-degree angle right here. And beta is equal to 40 degrees. And the side opposite a, which we call little a, is 10. Now what I want to do is I want to find the remaining angles, which is angle C, and the remaining sides, well, that would be B and C. So the first thing I'm going to do is realize that I have an angle and a side opposite it. So I know that the sine of A, which is 30 degrees, over the length of little a, which is 10, would be equal to the sine of B, and the sine of B I know is what is
40 degrees.
40 degrees, and this ratio to complete it would be over the side opposite B, which is
Little b.
Little b. And I'm just going to solve for b. I would do that by multiplying both sides of the equation by 10b, and I'd end up with 10 sine of 40 degrees is equal to what? Is equal to b times?
The sine of 30.
Very good. So I can find b. I would divide both sides of the equation by what? By the?
The sine of 30 degrees.
Very good. And so here is my representation for b. So it looks like b is, and I'm going to go ahead and just give us the answer here. I'm going to look over here and see what it is. It's approximately 12.9 to the nearest tenth, which is what I need to solve to. Now I also have to find the length of side of little c and angle c. But finding angle c is no big deal because I know that the sum of the angles in a triangle add up to
180.
180. So I have 180 degrees minus the angle I'm given, which is 30 degrees, minus the other angle I'm given, which is
40 degrees.
40 degrees, or I can just add the two angles and subtract them from 180. But what would that be? That would be what? That would be
110.
110. So 110 is the measure of angle C. Almost done. What am I missing? What do I still have to find? I have to find
You have to find little c.
little c. So again, I'm just going to use my law of sines. I'm going to go to the given, which says the sine of 30 degrees over the side opposite it which has a length of
10.
10, will be equal to the sine of 110 degrees over the length of the side opposite it, which is
Little c.
little c. And again, I'll multiply both sides of the equation by what? By 10c. So this gives me 10 sine of what? Sine of?
110.
Very good. And that's equal to c times what? Sine of
30.
30 degrees. And to complete this, I'll just divide both sides of the equation by
By sine 30.
sine of 30 degrees. And we're done. We just have to do this particular calculation. And if you're okay with it, I'll just look up the result. But the result here, little c is equal to, wait for it, 18.8. Thank you, and thank you. Let's solve the triangle for the missing side and angle measurements to the nearest tenth. Now with this triangle, we have alpha is equal to 35 degrees. Side opposite it, A, is 6. Beta is unknown. Side opposite it, B, is 8. Gamma is unknown, and the side opposite it, C, is also unknown. Now, whenever you have two sides in an angle, and one of the sides is opposite the angle, if that side is shorter than the other side given, so I'll mark shorter here and longer here, I want you to imagine this side here as being able to be drawn if I simply rotated it away from the angle instead. So with that image in your mind, imagine this being side 8, and this is B, except we'll call it B prime. This is still 35 degrees, but I'll call it alpha prime. And now I'll draw the side moving away from the angle. And so now I have A prime is equal to 6. My new angle here is beta prime. I have gamma prime and C prime, and I have a two triangle situation. So let's see if we could solve the two triangles. I'll start by using the law of sines. I know the sine of 35 degrees over the side opposite it, which is 6, is equal to the sine of beta prime all over 8. Now you may be wondering why I'm dealing with beta prime on this second triangle that I've drawn. And that's because I know when I solve, I will end up with a acute angle, and my blue triangle has beta prime with an acute angle. So if I proceed to solve, I'll find the sine of beta prime to be approximately 0.7648, and solving for beta prime, I find it to be approximately 49.9 degrees. Now I'll let you actually do the calculations there. Well, if I write in 49.9 degrees for beta prime, I see that I can find gamma prime because I know the sum of the angles in a triangle add up to 180 degrees. So, gamma prime could be found by taking 180 degrees minus the sum of the two angles given in this triangle, which is 35 degrees plus 49.9 degrees. So I find gamma prime to be approximately 95.1 degrees. So I will box it. I will place over here 95.1 degrees. And the only thing I have left to find is C prime. So I'll use this space right here to apply the law of sines again. And I'll have the sine of 95.1 degrees, because that is the angle opposite C prime over C prime. And that's equal to, and I'll use the given, and I was given 35 degrees, and the side opposite it is 6. So I'll have the sine of 35 degrees over 6. And solving for C prime, again, I'll let you go ahead and do the calculation, C prime is equal to 10.4. And I have solved one of the two triangles. I'll write 10.4 in right here. Now I also have my original triangle that I have to go ahead and solve for. And I'll start by the fact that I know that beta prime, well, that's approximately 49.9 degrees. So I want you to imagine, here's beta prime in quadrant 1. Now sine is positive in quadrant 1 and 2. So there's a second angle right here. I'll draw the rotation out to it, highlighting it very carefully here. That rotates so its terminal side is in the second quadrant with the exact same reference angle, 49.9 degrees. That angle is going to be found by taking 180 degrees minus 49.9 degrees. And that calculation would give us 130.1 degrees. This is what our new beta is going to be equal to. It's approximately 130.1 degrees. And I'll sketch that in right here, 130.1 degrees. Now to find gamma, well, I can do that quick enough. I know the sum of the angles in a triangle add up to 180 degrees. So gamma would be approximately 180 degrees. And I'll subtract the sum of the two angles that I know are in this triangle. That's an angle of 35.1 degrees, and my newly found beta, 130.1 degrees. So gamma is going to be approximately 14.9 degrees. See if I can write that in. That'd be 14.9 degrees right here. Well, all I have left is to find C, and again I'll use my law of sines. I'll take the sine of the angle opposite C, and that's the sine of 14.9 degrees over C, and set that equal to the given. So that's the sine of 35 degrees over the side length opposite it, which is 6. And again, I'll let you do the calculations, but C would be approximately 2.7. And notice I have solved my second triangle. Here's the 2.7. Let's find all possible triangles if one side has a length of 4 and its opposite an angle of 50 degrees, and we're given a second side of length 10. So since I know that I have a side and an angle opposite that side and another side, I'm going to go ahead and use the law of sines. So I'm going to start with saying that the sine of 50 degrees over the side that's opposite it, and that'd be of length 4, that should be equal to the sine of our missing angle, sine of alpha, over the side opposite alpha, which is 10. So if I multiply both sides by 10, I have 10 times the sine of 50 degrees over 4 is equal to the sine of alpha. So to find alpha, I'll just go ahead and take the arc sine of whatever I get as a result here. Well, what do I actually get? I find that the sine is going to be equal to, and it's actually approximately equal to, 1.915, at least to 3 decimal places. So I'm ready to take the arc sine of both sides, except I notice what? I notice that this number, 1.915, is greater than 1. And the range of the sine function, well, that is all values between -1 to 1. Sine will never be equal to 1.915. So I cannot possibly draw this triangle. There are no triangles possible with these dimensions. Now you may be saying to yourself, well, can't you sketch the triangle, at least try to? Well, sure I can. I can sketch a length side of length 10, I can try to project 50 degrees off of that particular side. But opposite the 50-degree angle, I know that the side opposite has length what? 4. And if I try to drop that side of length 4, I find I will never reach the opposite side. So, no triangles possible. Suppose two radar stations are located 20 miles apart and each detect an aircraft between them. The angle of elevation measured from the first station is 35 degrees, whereas the angle of elevation measured by the second station is 15 degrees. Find the altitude of the aircraft, and I'll call that altitude H, and I'll show H right here. We'll round the altitude to the nearest tenth of a mile. So as we go through the calculation, we'll actually round to the nearest hundredth of a mile until we get to our final answer. Now to find H, I'm going to divide this into really two steps. I want you to look very carefully at this side of my right triangle. And that side of my right triangle is the hypotenuse of it. So if I can go ahead and find that side, I can use my sine function for 15 degrees to find H, because sine is opposite over hypotenuse. Now the question is, how do I find A? Now to find side A, what I'm going to do is I'm going to resketch the triangle that is formed by looking at the plane and those two radar stations. I have a side A here, a side of 20 here, and I have angles. I have 15 degrees, and I have 35 degrees. And I suppose I can find my third angle very quickly by taking 180 degrees and subtracting away 15 plus 30, which is 50 degrees. And this is 130 degrees. Now look at this triangle I've written in blue and think to yourself, how would I find side A? Well, I can use the law of sines. I can take this angle and the side opposite it as a ratio. So I have the sine of 130 degrees over 20. And then I know I need to find side A, so let me grab the angle that's opposite side A, and that's angle has a measure of 35 degrees. So I'd have the ratio of the sine of 35 degrees all over A. So to solve for A, I'll cross multiply, or multiply both sides of the equation by 20A. And this gives me A times the sine of 130 degrees is equal to 20 times the sine of 35 degrees. And I want to wait to round until the very last step, so I'll divide both sides of the equation by the sine of 130 degrees. To find the length of side A and round it to the nearest, again, hundredth of a mile, so that I can go one decimal point past what I actually need to round my answer to, I'll take 20 times the sine of 35 degrees and divide by the sine of 130 degrees. So A is approximately 14.98. So I'll go ahead and ask you to look back at this right triangle, and if we know that A is approximately 14.98, if I draw my right triangle over here in red, just very roughly, crudely, what are we seeing? We're seeing 15 degrees is this angle. The hypotenuse has 14.98. And we're looking for the altitude, and that's what we called h. What I've done is sketch this triangle that I've seen. And I know that the sine of 15 degrees is equal to the length of the side opposite over the length of the hypotenuse. So let's substitute in for the side opposite. That would be what we're looking for, h. And a hypotenuse, that would be what we just found, 14.98. I'll multiply through by the common denominator, and I have 14.98 times the sine of 15 degrees. This is what h is equal to exactly. Rounding to the nearest hundredth, I find h to be approximately equal to 3.88. Well, the final step is to round the altitude to the nearest tenth. H is our altitude. Rounded to the nearest tenth, we would say h is approximately 3.9. So the answer to our question, what is the altitude of the aircraft? 3.9 miles to the nearest tenth of a mile. Solve oblique triangles using the law of sines that gives ambiguous results. If you're using the law of sines and you're given a side-side angle, and you realize to yourself, gosh, what's the best case scenario? I'll solve the triangle. And that happens when we have a situation where we have an angle, A, the side opposite it, A, is greater than the other side given. And then there's only one triangle I can sketch. But if my side opposite is shorter than my altitude, I can't sketch the triangle because I can't really reach that other side. And if my side opposite is exactly equal to my altitude, I have a right triangle. None of that is what we're talking about. We're talking about the possibility where I'm giving you the case where my side opposite is going to be shorter than the other side. So here's A and here's B. And when that happens, I can create two triangles. It's called the ambiguous case. One triangle I've sketched, but the other triangle is formed by rotating A back toward the angle. And there's my second triangle. Now there's a lot of information there, but the key is to recognize that you have this ambiguous case. And all you really want to do is say to yourself, gosh, if I have an angle, angle A, and if my side opposite it, which I'll call little a, is shorter than the other side given, then I may be in my ambiguous case. So take a look at this problem. Little a is 8, little b is 10, and alpha is 30 degrees. So take a look at alpha, which is given. The side opposite it is 8, and the other side is 10. So the side opposite is less than the other side. This creates two triangles. And when this happens, what you always do is solve the outside triangle first. And that means when we rotate A, we rotate it away from the angle alpha, and we get this triangle in green. Now, as far as how you solve it, there's no mystery there. We do what we always do. So I'll go ahead and take my given. Remember, alpha is what? Alpha is
30 degrees.
30 degrees. So I'll take the sine of 30 degrees divided by the side opposite it, which is
8.
8. And I know I'm given a side of length 10.
Right.
So in the numerator would be the sine of the angle opposite it, which is the sine of
Beta.
Beautiful. So let's find b. The way we do this is we solve for the sine of b. And the sine of b would be 10 sine of 30 degrees over 8. And then we would take the arc sine of that particular ratio. And so the arc sine, b, would be the arc sine of that 10 sine of 30 over 8. And I'm just going to write in whatever that value happens to be, and it's 38.7 degrees. You want to be in degree mode. So now I have this angle, 38.7 degrees. Now once I have beta, I can find gamma. I would just take, what, 180 and subtract away what? Subtract away?
Subtract away 68.7.
Beautiful, because you would just add those two angles up, wouldn't you?
Yes.
And when you do that, you would find alpha to be approximately what? Approximately
111.3.
Very good. Degrees.
Right.
And all we have left is to find side little c, but again, we're just using the same methods we always do. We take the sine of the angle opposite c, which is
111.3.
good, over c, and that's equal to, and I'll pick the given that I had, the sine of 30 degrees over what? Over
8.
Over 8. And when you solve, you find that c is equal to, and I'll just write it down for us, 14.9. So you found one triangle, but we have to find the other triangle.
Is that a length for C?
Oh, it is a length. Thank you for catching that. Very good catch. Very good. Now let's look at solving for the other triangle. Now we can create a second triangle, and the way we do this is we rotate A back toward the angle, and that creates this triangle that I'm highlighting here. So now instead of solving for beta, gamma, and C, I'm going to solve for gamma hat, beta hat, and C hat. And the way I'll begin is to take a look at beta hat right here. And I'm going to remember that we had a measure for beta before. Beta was, I'm going to look back to my notes, beta was 38.7 degrees. Now, if you think about that, that came from the fact that we knew the sine of beta and we took the arc sine. And we found that angle 38.7 degrees. But see, with the sine function, which is positive in quadrant 1 and 2, if 38.7 degrees is a reference angle, then this here rotation, which is very important to us, could also have that same sine of beta hat. Exact same value. And so that rotation, which is where we're going to begin, beta hat, is found by taking 180 degrees minus 38.7 degrees. And that would be what? That would be
141.3.
Beautiful. So now I have beta hat. And that's this angle right here, 141.3 degrees. Well, now I have two of the angles in my triangle, which I'll kind of shade my triangle right here a little bit for you. And so I know that gamma hat would be found by taking 180 degrees, which is the measure of the angles in a triangle, and subtracting away my alpha, which was 30 degrees, added to the measure of my beta hat, which is 141.3 degrees, and that's approximately, boy, it's not going to be much. It's approximately what? It's approximately
8.7.
Beautiful. So there's 8.7 degrees. Almost looks like it, doesn't it?
It does.
And now to find the last piece of information, which is what? Little c hat, is that right?
Right.
I just do what we've been doing before. And what we've been doing before is taking the sine of the angle opposite c hat, the sine of 8.7 over c hat, and setting that equal to, and I'll take the sine of alpha over a since that was given. That's the sine of what? Sine of?
The sine of 30 over 8.
30 degrees over 8. And then I just solve for c hat. So c hat turns out to be approximately 2.4. So I end up with two triangles, which is why this is called the ambiguous case, and I solve for each triangle separately. Thank you. We're going to find the angle A for the given triangle where we're given three sides. Side A is 20, side B is 25, and side C is 18. So since we're not given the measures of any angles at all, we'll use the law of cosines. And the way the law of cosines is set up is, since we're looking for angle A and we have the side opposite it, we start with a squared, and that's equal to the sum of the squares of the lengths of the other two sides, b squared plus c squared, minus 2 times bc, times the cosine of the angle that's opposite side A. And we have some information. We know that side A is 20, and this has to be opposite angle A. So angle A is opposite the side of length 20. As far as B and C are concerned, that's just our other two side lengths. B is 25, C is 18. So I'll make those substitutions where I see B and C into this calculation. So let's write down what we have. We know we have 20 squared is equal to 25 squared plus 18 squared minus 2 times 25 times 18 times the cosine of A, and the cosine of A is what we're looking for. So I want to isolate the cosine term. So I'm going to first start by trying to isolate this term that I'm underlining. How do I do that? Well, I'll go ahead and start by trying to grab numbers. In place of my 20 squared, I'll write it as 400. In place of 25 squared, I'll write 625. In place of 18 squared, I'll write 324. And then it turns out that if I take twice 25, that's 50, and 50 times 18 is 900. So I'll have 900 cosine of A. And like I say, I do want to isolate this negative 900 cosine of A. So to do that, I'll go ahead and take 400, subtract away 625, and subtract away 324. And that's equal to negative 900 cosine of A. Well, 400 minus 625 is negative 225 minus 324. Well, that's negative 549. Negative 549 is equal to negative 900 cosine of A. Now it's looking like an equation that I can quickly isolate the cosine of A by simply dividing by negative 900 on both sides of the equation. So the cosine of A to two decimal places, cosine of A is approximately 0.61. I'm almost done. All I have to do is what? All I have to do is find A. So I'll take the arc cosine of 0.61, and actually A will be approximately that value. So A is approximately, and we have 52.4 degrees. Solve oblique triangles using the law of cosines. Law of cosines lets you find the length of a side by relating it to the angle that it's opposite and the other two sides in the triangle. And the way it works is like this. You take an arbitrary oblique triangle, and I'm just going to drop a perpendicular. I'm going to ask you to focus on this right triangle right here. And what I'm going to do is I'm going to pick a side. And the side I'm going to pick is this side right here. I'm going to shade it. And that side has length A. So I'm going to write that side's length by simply doing nothing more than taking a look at the distance formula between these 2 points that I'm highlighting. Now, for the coordinates of those 2 points, what are they? Well, this length right here, well, that's a length of C. So the coordinates at the vertex of angle B is C0, C0. For my other point, the coordinates are x, y, where here I have an x and here I have a y. Let's see if we can find out what x and y are in terms of the parts of the triangle. So I can do that. I know the sine of A is equal to the opposite over the hypotenuse, and so the opposite of A would be what? It would be
y.
So I have y over what? Y over?
Y over b.
So it means I can find y in terms of the parts of the triangle. Y is equal to what? It's equal to?
It would be b times the sine of A.
Sine of A, very good. And similarly, I can go ahead and say the cosine of A would be what ratio?
Would it be x over b?
Adjacent over hypotenuse, x over b. So I know x in terms of the other parts of the triangle. It would be what? It would be?
It would be b cosine of A.
Very good. So now I'm just going to apply the distance formula for A. And the distance formula, just to remind all of us, is found by taking the square root and you subtract the x coordinates and you square it, and you subtract the y coordinates and you square it. Well, for us, the distance we're focusing on is the length of side A. So I'm going to write A is equal to the square root of, then I'm going to subtract the x coordinates. So I have x minus c. Now, x is what? X is?
We found it to be b cosine of A.
Very good. Minus c, and that's squared. And then I'll take y minus 0. But y we found to be what? Y we found to be?
b sine of A.
No, ma'am. Or b sine of A. Yes, ma'am. Sorry. And I'll subtract away what? I'll subtract away?
A 0.
0. Very good. So now I'm going to do two things. I'm going to square both sides of the equation. And then I'm also going to multiply through the parentheses. I'm going to square my binomial. So I square the first term. That's b squared cosine squared of A. And then I have minus 2 times b cosine of A times c, which I'll write as 2bc cosine of A. And then plus the last term squared, plus c squared. And so, for those of you following at home, we just went ahead and just multiplied this through. Then what will I do? Well, I'll go ahead and take b sine of A and subtract 0. What do I get?
b sine of A.
And I'll square it. That gives me
b squared sine squared of A.
very good. So I'm going to write that in, b squared sine squared of A. And I do notice something, right? You notice something, huh? And that is that we have b squared sitting here and here. So I'm going to factor that out. Can you kind of look ahead and see what happens when I factor it out? I end up with a squared is equal to b squared. And when I factor it out, what's in the parentheses?
It would be cosine squared of A plus sine squared of A.
Very good. And then I'll just write out the rest of what I have, which I want to say is plus c squared minus 2bc cosine of A.
Right.
Now, I know from the Pythagorean identities, sine squared of A plus cosine squared of A is
1.
1. So this piece right here is just what? It's just
1.
Just 1, isn't it? So what do we end up getting? Well, what we end up getting is our law of cosines, which is a squared is equal to b squared plus c squared minus 2bc cosine of A. Now I'm just going to circle that. And what we see is that A, B, and C were just kind of arbitrarily placed on the triangle. So in the much broader picture, what we can basically say is that all we're really doing is taking any side and saying it's the sum of the squares of the other two sides minus 2 times the product of those two sides. And then A, this A, is opposite my side of A that I'm actually isolating. That's my law of cosines, which looks just like this. So the law of cosines simply states that if you take the square of any side, I'll pick now side C, a different side. The way I'll find it is I'll take the sum of the squares of the other two sides minus 2 times the product of the length of those two sides times the cosine of the angle that's opposite side. Thank you and thank you. Suppose a boat leaves a port, travels 10 miles, we'll pick north, turns 20 degrees, we'll pick northwest, and travels another 8 miles. How far is my port from the boat? Here's the port, here's the boat. Notice we have a triangle. And if I go ahead and look at this angle right here, this angle I can find by realizing that along a straight line, that measure is 180 degrees. And if I subtract 20 degrees, I find that angle to be 160 degrees. Notice what I have is two sides, an angle between them, and I'm looking for a side that's opposite that angle. That's the law of cosines, isn't it? That's nothing more than a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of that angle that I'll just call alpha. So let's make the substitutions and see if we can solve for a. So since I'm looking for a, I know that in place of one of the sides, I'll put a 10. In place of the other side, I'll put what? I'll put an 8. So I'll do that in 2 locations in this formula. And the cosine of alpha, which is the angle opposite a, would be the cosine of 160 degrees. Do you see the formula forming? So we have a squared is equal to, and I have 10 squared plus 8 squared minus 2 times 10 times 8 times the cosine of what? Times the cosine of 160 degrees. Now, as long as my calculator is in degree mode, I can go ahead and enter this equation just as I see it in the calculator. And I have a squared is equal to, and this will be approximately to 2 decimal places, 314.35. So taking the square root of both sides, I find a to be approximately 17.7 miles. Let's find the area of the triangle using Heron's formula. And this triangle has side lengths of 10, 15, and 7. A is 10, B is 15, C is 7. So what Heron's formula states is that the area is going to be the square root of this calculation. Now bear in mind when I say S, S is going to be 1/2 of the perimeter. So the area is the square root of S times S minus A times S minus B times S minus C, and that whole product is inside of the square root. Now the first thing I have to do is find S. But again, S is nothing more than 1/2 of the perimeter. So S is going to be A plus B plus C divided by 2. Well, we know A is 10, so we have 10 plus B is 15 plus 15. C is 7 plus 7, so we have 10 plus 15 plus 7 all over 2. So it looks like S is equal to 10 plus 15 is 25, and 25 and 7 is 32. We have 32 over 2. And so if I go ahead and reduce, I find that half the perimeter is going to be 16. So I'll make the substitutions. In place of S, I'll put a 16, and that will go in 4 locations. In place of A, I'll put what A is equal to, which is 10. I'll put what B is equal to, which is 15. And lastly, I'll put what C is equal to, which is 7. So here's my calculation. Area is going to be the square root of, and you have 16 times 16 minus 10 times 16 minus 15 times 16 minus 7. So the area is going to be the square root of, we have 16 times 6 times 1 times 9. So it looks like the area is the square root of the product, 16 times 6 times 9. So that's the square root of 864. So if I'm finding the area exactly, the area itself is the square root of 864, which is the same as the square root of 144 times the square root of 6. So it looks like the area is 12 times the square root of 6. And if I was approximating this to 1 decimal place, I could say, or 29.4. Find areas of oblique triangles using formulas associated with their sides, called Heron's formula. Well, if I want to find the area of an oblique triangle, which is just a triangle that's not a right triangle, what I'm going to do is use Heron's formula. And the formula up here basically says you take the square root of, and you have these four numbers you're multiplying. S, that's 1/2 of the perimeter, or the distance around the triangle. And then you multiply it by that value of S minus the length of side A times the value of S minus the length of side B times the value of S minus the length of side C. So to use this formula, what would I have to give you? I'd have to give you the lengths of the three sides. So the first thing I'm going to do is I'm going to go ahead and take a look at using Heron's formula, and I'm going to find S. And S, well, that's just 1/2 of the perimeter. Well, the perimeter is just the distance all the way around. So that would be 1/2 times, well, what would be the distance all the way around?
Would it be 10 plus 16 plus 20?
Very good. Now let's see, 10 plus 16 is what? That's
They're 26?
plus 20?
46.
So what is S? S is what? S is?
S is 23.
23. Very good. Now I can begin. To find the area, what will I do? Well, to find the area, what I'm going to do is say the area is equal to the square root of S, which I just found. That was what? That was?
23.
23. Then I just take 23 and subtract away the length of each side, separately. So it'd be 23 minus,
Minus 10.
okay, then it would be 23 minus,
Minus 16.
okay, and then it would be 23 minus,
Minus 20.
very good. So let's see if we can simplify what's inside the radical. I have 23 times what three numbers times?
Times 13, 7, and 3.
Very good. So when you calculate it, please tell me what 23 times 13 times 7 times 3 is.
It is 6,279.
Beautiful. And so the area of this triangle would be the square root of that number, which I think it's going to be approximately. I don't think it's going to come out exact. So let's go ahead and go to 2 decimal places. What would that be?
79.24.
Beautiful. And that's Heron's formula. Thank you, and thank you.